Okay, welcome. My name is Jack Haben. This will be a demonstration of a return to libc attack based upon SEED Labs. So this is for Cyber 4420 Section 1 Cyber Operations. So full disclosure, this video is for educational purposes only, and I am not liable for any damages that could be caused by using any of these demonstrations. All right, so like I mentioned, my main resource for this was seedsecurity-labs.org. It's a great resource for hands-on experience in security. This will be performed on an Amazon virtual machine in the cloud, the Seed Ubuntu version. The seedsecurity-labs.org goes into that more, how to set that up if you're interested. But it was very convenient. I had a lot of fun doing it. And the labs get you a lot of hands-on experience, and they also give you a lot of good information, but they do require a lot of research and a lot of trial and error, and there are a few spots where I got stuck, but I've done a few of these, and I always end up learning a lot. So it was a good experience. I had fun, so I'm excited to demonstrate this. So the return to libc attack is a buffer overflow attack. It's a variation of a buffer overflow attack. Generally speaking, in the past, a buffer overflow attack would overflow the buffer with malicious shellcode, then make the program jump to the stack, and that's where it would execute the malicious code. That's traditionally speaking. Now, a lot of operating systems have taken countermeasures to prevent this. So this video will demonstrate a variant of your traditional buffer overflow attacks, because the return to libc attack, it actually is a little bit different, and we'll see why. But some of the security measures that modern operating systems have used is they've made the stack non-executable. So even if someone makes the code jump to the stack, they won't be able to execute it. Now, the return to libc attack shows that it's okay from the perspective of the attacker, because we can execute the attack without even executing anything on the stack. That's what the return to libc attack does. So, and it doesn't even use any shellcode. So what it does is it causes a vulnerable program, instead of going to the stack, it says it returns to the libc library, which is already going to be loaded in memory, and takes advantage of that. And that's where the exploitation happens. All right, so to make this possible and a little bit more simple, what we're going to do is, one of the countermeasures modern operating systems usually take is they make the address space kind of randomized to kind of make this harder to prevent these type of attacks. So we're going to turn that off just to make things more simple. But however, we are going to keep the non-executable stack turned on. So we won't be able to execute anything on the stack. So this will prove that the return libc attack is a variation, and we will be able to carry out the attack even though the non-executable stack is going to be turned on. Okay. All right. So what I'm going to do now is turn those settings on. So here we are. So this is where we're at. So I'm going to first run a couple commands to turn on the settings. Like I said, we're going to turn off address randomization. That's what this code will do. Okay, so that is turned off. But we are going to also run this which helps with user IDs. Excuse me, this helps, so this is more for Ubuntu 16. I'm running Ubuntu 20, so this doesn't apply as much. But if you are running Ubuntu 16, you want to do this command, because it has has a protocol in there that would prevent the exploitable file from giving up privileges. So I'll get more into that in a little bit. So that's the first two commands we're going to go with. Now, let's look here. Let's set up the scenario a little bit. Let's pretend you are on a system and you are maybe a spy, or you want to do something malicious, or you want to attack this system. And you notice, let's say, for example, you don't have root privilege. You have very low privileges. Right now, I'm going to assume I'm not going to use any root privileges. So this file you see here, top secret, you need to have root privileges in order to open this file. So I'm going to try to open it right here. And as you can see, I got permission denied. So what we can do is take advantage of this program, the retlib.c program, because this has a vulnerability in it that we will be able to exploit. So what that will do is allow us to exploit that in order to gain privileges, in order to open up this file and do any other root things as well, because we're going to get a root shell. So I'm going to show you how to get that. So again, who am I? Right now, I'm just Ubuntu, just a user. So I want to try to get the root privilege to open up this top secret file. All right, so let's take a look at this vulnerable program a little bit. So let me open it up here. All right, so here's our vulnerable program. It's going to call this function, the BOF function, buffer overflow, and it's going to send in our information through this bad file. It takes that as user input, so we can take advantage of that and send in malicious code through this bad file that will cause this program to give us a root shell, because right now this program has root privileges. So we don't, but we're going to try to take advantage of the fact that it does. So right now, let's create this bad file. So I'm going to create that bad file. It's just going to be a blank file for now. All right, there we go. And there it is. All right, now in order to compile this vulnerable program, we have a make file here. So let's take a look at that. Excuse me. All right, that didn't work. Might help if I actually include the file. There we go. All right, so here's the make file. Now the lab uses a default of 12 here. It does encourage you to ask your professor for a different number there, which I did. So we're going to change that. Instead of a 12, I asked Professor Hepp for a random number between 10 and 800, and I was given the number 386. So we're going to put that in there. There we go, 386. And let me save that. There's one other thing I wanted to do there. We also need to compile this file in a version that allows us to see some of the assembly code instructions. So in order to do that, we're going to throw a flag out here, and that flag is going to just be a G. All right, got that. Okay, so let's take a look at that one more time. This is just our make file. So this is 386. That's going to be the size of our buffer, and that will be put in here. This N, that's our 386, and randomizing that, instead of just doing the default 12, just helps with the lab experience and gives you a little more of, a different experience than anyone else would have. So that changes the address space of the memory a little bit. So my experience won't be the same as anybody else who does a different number there. It'll be a little bit customized. Now this is a setting that most operating systems have these days called stack guards. We're going to turn that off. But again, we're going to keep the non-executable stack on to help us. To show that this is not your typical buffer overflow, it's a variant. And we don't even need the stack. So we got that. And this program does have root privilege, which we're going to try to take advantage of. Okay, so that's the make file. Now let's make it. All right, so make file. Boom. All right, there, we just made our program, our vulnerable program right there. All right, so let's take a look. So I mentioned earlier in this vulnerable program, okay, it takes in a bad file, and we're gonna send bad code in there to try to take advantage of this guy. So how do we make this bad file? Well, we were provided another program, this exploit Python file. So let's open that up. This is this will create the bad file for us. It'll write out this contents of this to the bad file, which will send it to that retlib program. So what we need to do is now in our vulnerable program, we need to find a few addresses, which will help us take advantage of things. We need to find the system address. We're gonna put that here. We need to find the exit address, which we'll put that here. And then we need to find the bin/sh address. We're gonna put that there. We also need to figure out what these X, Y, and Z numbers should be. So we're gonna explore how to do that here next. Okay, so now we need to find those things. We need to find those functions and place them in the right spot. And how do we do that? All right, first, what we can do is to do that, to find those things, we can take advantage of the debugger. So right now, we're gonna pull up this retlib program in the debugger by doing this, GDB, and then we're gonna put this flag on there, Q for quiet mode, and then we're gonna bring up that program, retlib. Now, we're gonna put a breakpoint on the main function. Do that, and we'll run the program in the debugger. And now we're kind of in the file, it's running, so everything's loaded in memory, so we can find where those functions lie. So first, we're gonna print out where the system function is. Okay, here's the address space of the system function. So I'm just gonna copy this. I'm gonna save it here for later. Put that in our exploit file to make our bad file. I'm gonna save it there for now. We're also going to find that exit function where that is. And this is the address for where that's gonna be. Okay. All right, so there it is, we got that. That's the exit address. All right, so now that's all we need from there. We're going to quit from the debugger, yes. Now, we need to find where the shell is gonna be. So in order to do that, we're gonna take advantage of something called the environment variable, and we're gonna run this command, which will help us find where to the address of where we should call our shell to try to get that root shell. So we're gonna run this command, and then we're gonna run this environment command that will help with that as well. And we were given, we've got that put in it. Now we were given by the lab a little program called this PRT environment.c program. So we're gonna run that, and that's gonna tell us where the address is for our shell. So you can see it here. It's very simple. It just, all it does is it gets the environment of our my shell, which we just put in here, and it's gonna tell us the address space of where that is, so we can use that. So now we'll just run that quick, that little PRT env program, and there it is. This is the address space of the shell. So that's what we need to copy, and we have that. So we're gonna put that here. We're gonna put an OX in front of it. All right, now we are ready to put that information in our file, in our exploit file. So we'll do that quick. So again, that information is going to go in here. So we've got this, which is where our shell address should go. So let's put that in there. Get rid of the old one. And then this is the system address. We're going to copy in that address, which we just found from the debugger. Okay. Get rid of the old one. There we go. Now we're going to copy in. We're going to copy in this one. This is the exit address or exit function. So paste that in there. Uh-oh, I didn't do that right. That one is the exit address. This one is supposed to be the shell address, which is right here. So let me go back and fix that. Okay. Paste that in here. Okay. Now we just need to find this X, Y, and Z and figure out what that should be. So that's our next step. So we're going to save this. Okay. Now to find what those variables should be, the X, Y, and Z, we can use our debugger, and this time we're going to get into some of the assembly language markers that will help us find what those variables should be. Anyways, assembly language has these things called prologues, epilogues, which take place during functions, and they have these certain markers on there, which kind of set things up for calling the next function. So we're going to take advantage of that to figure out how far we should set those functions apart. So let me pull that up here. We already made our bad file, so we're going to again call the debugger with our program. All right, there we go. Now this time we're going to set a breakpoint on the function in our vulnerable program called BOF, and set that breakpoint. Okay. Oh, symbol table is loaded. What is that? Just a second here. Sorry about that. So I put in the C here. That's the C version. We actually have to put in the compiled version. So that's why it's giving me trouble here. So let's try that again. Get rid of that .c. Just put in the compiled version there. So there we go. Now we're going to set a breakpoint on the BOF function, the buffer overflow function, and then we're going to run it in the debugger. And then what we'll do is we have to put in this next code, which gets us a few steps beyond what further in the code in the debugger. And now we're ready to look for those assembly markers, which gives us hints as to where we should set up our bad files. So the first one we're looking for is this EBP. So we're going to print the location of that by doing this P for print EBP. Boom, there is the location of that. Now the next thing we want to know is the location of the buffer. So to do that, we print ampersand buffer. Boom. All right, so there's that. Now to figure out, we want to find a difference between these two as far as how far apart they are. So we're going to do this P/D, and then you take the first one, and then you minus the second one. Run that, and there it gives you the 398. That is where we want to start things off as far as our X, Y, and Z's, and I'll explain that here. So let me get out of the debugger and let me open up our exploit file. All right, so the first one we want after the buffer overflows, the first one we want the system to call is the system function. And so that 398, we're going to add 4 bits to that. Just that's how the offset kind of works out. So we're going to put 398 plus 4, which gives us 402. Now after that, we're going to add 4 more bits. So we want the exit function to call, because that will kind of prevent a segmentation fault, and so that things will, proceed cleaner. Won't raise any flags. Will be more covert that way. So we're going to add 4. So 406 is where we put the Z variable. And then lastly, the last thing we want to go to be called is the shell that will give us root privilege. So we had 4 more bits, and we put that at 410. So let's save this. Right, quit. Okay. All right. Now we're cooking. So now we are ready. So first thing we need to do is clean that up. And now what we're going to do is we're going to call our exploit program to load up our bat file. So let's do that. All right. And then we're going to exploit py. That's the program. Run that. So now our bad file has been created with the information and variables and address spaces that we put in there. And that's what we're asked to feed into the vulnerable program. And we're going to call the vulnerable program. It's going to read the information from here. It's going to cause a buffer overflow, and then it's going to line things up perfectly so that when the buffer overflows goes, it's going to jump to that libc library, that system function in libc library that's already loaded in memory, not the stack. It's not going to execute anything on the stack, but then it's going to jump to that function. It's going to call the system function. It's going to exit and then pop out a root shell. So let's do that. So we're going to just call, sorry if you hear children screaming in the background. I promise they're just normal household things going on here. So, all right. So retlib program, boom. And it didn't work. So let me see. Oh, you know what? Dang. I know exactly what happened. We forgot to do one thing. I forgot to do one thing, and that is in our exploit program. All right, so let's do this. Exploit this 300. Since I was given a number over 300, I was given a 386 for the size of my buffer. We got to make that bigger. That's all that happened, I promise. So let me fix that here. So get rid of let's make that 500. So there we go. That gives us enough space. All right, so I'm gonna save that. All right, now we're ready. All right, hopefully this will work now. Okay. That didn't work either. What happened? All right, you know what? I gotta redo the exploit program. Stick with me. I promise. This is gonna work. I promise. So we just have to call the exploit program. So Python, we're gonna recompile that one, that exploit program, because now it'll fix the change we just made, and that will send that into bad file. So now, boom, there we go. Finally, all right, we got the shell. We got the root shell. So let's make sure it's the root shell. Just ID, look, root. We'll say, who am I? Who am I? Root. I'm root. I got it. All right. All right. Now, what we can do, where's that file? That top secret file. Now we can see what's in there. So let's cat that baby. Top secret. Boom. There's a secret message. Alice, meet me at Taco Bell at 3 p.m. from Bob. There, we did it. We got the root shell. We exploited the program. That's it for this demo. So this was very fun. Thanks for sticking with me. And yeah, tried to do it in one go. I had to stop there once, but there's a few moments along the way, but we got her done. So thank you so much. And this was a lot of fun. It's a good learning experience. I always learn a lot from these SEED labs and have a good time. So thank you. Sayonara.